Good day, everyone. My name is Ross Eldridge, and I'm going to be going over my presentation for the failure modes and effects analysis for my system. Just a reminder, my system is the power distribution system for a natural gas compressor station. Before I get into the analysis, I just want to go over a couple of assumptions that I made about the site. The first assumption is that the instrumentation essentially will be working correctly at all times. This is to say that all necessary relay contacts will open and close as they should. The wiring from the contacts back to the PLC is all good, and the PLC is running at all times. It doesn't fail. In general, that's what I'm saying. I think I have a couple of instances where I'm saying that relay contacts fail. Secondly, would be the preventative maintenance schedule performed at the site. From my experience in coal mining, they typically have a preventative maintenance schedule of 3 months, 6 months, and 1 year, with each of those maintenance schedules going up with increased levels of scrutiny, which with each one, your 3 month would be a general one, whereas your 1 year would be the pretty detailed, getting down into the nitty-gritty and making sure everything is running. Going into the analysis, if you were to look at my FMEA spreadsheet, you would see that there are quite a bit of repeats as far as failures that can occur. And this is kind of to be expected. In a power distribution site, if you look at it really high level and don't really look into what's going on, essentially what you have is a series of switches that are going from your high voltage down to your load. And obviously you have transformers in the middle, but most of the equipment you have between your utility or your generator feed and your load is just a series of switches. For example, you have your main transformer, and then downstream from that you have an automatic transfer switch, and then downstream from that you have your switchboard, which has a main breaker and then just a buswork of different loads that come off of that, and that's essentially your power distribution network. In looking at my FMEA, there were 3 points of particular high risk. That would be the main transformer, the generator, as well as the grounding system. For the transformer, there are a number of good failure points on there. The first one you'll see will be your bushings coming in, and that would be from your utility high voltage feed coming down into your transformer core. Those are experiencing the elements, the wind, the precipitation, flying objects in the wind perhaps, and essentially these are just conductors that are surrounded by a glass insulator, and if these insulators are to crack, or if you get build up a material that is conductive, you can form another path to ground that the current would prefer to take, as it'll be a lower resistance path. Another failure point in the transformer is the transformer oil. In kind of in the same vein, if the bushing becomes loose and you get water or dirt getting into your transformer oil, that'll reduce the dielectric properties of the transformer oil, and that lends itself to obviously the breaking down of the oil, and that's also used as a cooling medium. But also you run the risk of turn-to-turn shorting in your coil, phase to ground shorting within the transformer, and if any of these events occur, you'll more than likely trip your main breaker for that transformer, and your site will lose power. So that's a serial kind of choke point that I'll be investigating later. Um, the next point was the generator. Um, this is kind of where the assumption that the relay contacts will be working does not come into play. Um, it's very dependent. The generator starting is very dependent upon receiving the signal from the undervoltage or loss of voltage relays upstream that there is a problem and there's a loss of voltage. So if the generator doesn't get that message, it won't start and your site will lose power. Um, another thing that needs to occur is the generator needs to be exercised, even if utility power is really strong and you're rarely, if ever, losing power. You still need to start the generator, and even if it's at no load, you need to run it and get oil circulating through everything, make sure everything's lubricated, make sure the parts aren't cold welding or something out of the ordinary. You just need to run it every once in a while. The third point of risk in this system is the grounding system. And in a compressor station with all the gases that you're dealing with, you can get a highly corrosive environment, especially in the low-lying areas if you're compressing a heavier than air gas or especially a liquid. And when these they sink down into the low points, obviously, they can permeate into the ground and get into your ground grid and corrode it to such a point that you will lose your resistance to ground. And that can create dangerous touch and step potentials. A touch potential is essentially if you're standing on the ground and you reach out and touch the equipment, that would be a touch potential. And that can, in the event of just normal operation, not a lightning strike, you can have up to whatever the utility voltage is. And I believe at this site it's 25 kV. So you'd have 25 kV between your hand and your feet. Step potential you see more with lightning strikes. When the lightning strikes the ground, you get voltage potentials in essentially a radiating pattern. So if you were to take a step, it's usually set about 3 feet as a step. You can get dangerous voltage levels between your feet that'll go up through your body and back down. So those are three key points that need to be kept in mind in the design. I guess just real quickly, my criteria in my FMEA, my probability of failure occurring, I went 1 to 6, with 1 being never going to happen and 6 being it's going to happen all the time. Severity 1 to 6, 1 being no effect on either human health, animal health, equipment health, where a 6 is a catastrophic failure. Many lives are lost. Equipment is just irreparably damaged. And then detection, I went from 1 to 6, where 1 is it will absolutely be caught, and 6 is the fault can go on forever. And a lot of these faults in my detection dormancy period, I said were real time, because many of these things are being monitored by the PLC essentially in real time with a scan time of up to about 500 milliseconds, so about half a second. So these are being read almost continuously. So many of these events will actually be caught relatively quickly. But one that wouldn't be caught particularly quickly would be the grounding. If you have an increase in your resistivity of your ground grid, that wouldn't necessarily be caught by the PLC in real time, or even in a PM situation, a preventive maintenance situation. So that needs to be added to the preventive maintenance schedule, probably on a yearly basis, just to make sure that your resistance to ground is within tolerances, and if it's not, it needs to be repaired immediately, because that could be as far as electrically, your largest danger within this site. Hopefully I have taken care of the requirements of this presentation. If you have any questions, leave them in the comments or put them up on the discussion board. Good luck, guys.